This video lecture is going to look at how to time traffic signals. Optimal traffic signal timing requires allocating effective green times to competing approaches in an optimal fashion. We need to know what are the arrival patterns, on what basis should the signal timing be optimized. So, are we trying to minimize delay, minimize number of stops, minimize queue length, and what other factors are at play such as coordination? Now, there are many factors. This example is going to simplify them and look at minimizing vehicle delay. So in this problem, we have a pre-timed two-phase traffic signal which controls a four-way intersection with no turning permitted and zero lost time. The eastbound and the westbound movements are on the same phase. Similarly, the northbound and southbound movements are on the same phase. Saturation flow is 1,700 vehicles per hour. The cycle length is 60 seconds. Flows are as shown in the diagram. Eastbound is 500, westbound is 600, southbound is 700, northbound is 800. And these are in vehicles per hour. Determine the effective red and green times for each phase to minimize total vehicle delay. Compute the total delay per cycle. The first thing we need to do is put arrival and departure rates into common units of vehicles per second, and then compute intensity. The rate, or lambda, for each movement is the number of vehicles on that movement per hour divided by the 3,600 seconds per hour. And this gives us, in the case of the eastbound movement, 0.138 vehicles per second. You can see the values for the other movements. Similarly, we're computing the intensity, or the lambda over the mu. Now the mu, or the server rate, is 1,700 vehicles per hour, or 0.472 vehicles per second. So we can compute our intensity for the eastbound movement as our lambda of 0.138 over our mu of 0.472, which gives us 0.292. And we can do this for all of the movements. And the third column is a calculation that will be useful to us a little bit later. So, the total delay can be calculated as the sum of the delays on each approach. You'll recall that the delay on each approach is the lambda, or the arrival rate on that approach, multiplied by the red time squared, divided by 2 times 1 minus the rho, or the intensity of that movement. Now we have 4 movements, so we have 4 delays that we have to add together. So in that equation, the unknown is the red time. That is what we're trying to solve for. This looks like 4 variables. We have the red time on the eastbound approach, the red time on the westbound approach, the red time on the northbound approach, and the red time on the southbound approach. However, it is really just one, because the red time on the eastbound approaches are the same, and the red time on the northbound and southbound approaches are the same. Further, we know that the red time on the eastbound approach is equal to the cycle length minus the red time on the northbound approach. So we only have one variable here. We can substitute our long equation and get an expression that the total delay is equal to 0.0974 times the red time on our eastbound approach plus 0.1228 times our red time on the westbound approach squared plus 0.209 times our red time on the northbound approach squared plus 0.165 times our red time on the southbound approach squared. Now, I mentioned that we had a calculation that we wanted to do to simplify things. I've defined the variable x to equal lambda over 2 times 1 minus rho to simplify our calculations here by solving that beforehand. Now, we take our total delay expression and we can rewrite it in terms of our red time on the eastbound approach and simplify this using standard algebra, and we get our total delay is 0.6 times our red time on the eastbound approach squared minus 45 times our red time on the eastbound approach plus 1,346. Now what we need to do, our objective is to minimize the total delay. How do we minimize a function? Well, we use the calculus. We take a derivative and set it equal to 0. So we're taking our derivative of our total delay with respect to the red time on the eastbound approach. Set that equal to 0, and that is 1.2 times our red time on the eastbound approach minus 45. Now this gives us a red time of 37.2 seconds. Because the effective green time is 1 minus the red time, That gives us a green time of 22.5 seconds on the eastbound approach. The northbound approach has a red time of 22.5 seconds and a green time of 37.2 seconds because of a finite amount of time in a cycle and no lost time assumptions. And our westbound approach has the same red time and green times as the eastbound approach, and the southbound approach has the same red time and green times as the northbound approach. So, if we know our red times, now we can substitute back into the total delay equation, and that gives us a total delay of 547 vehicle seconds. Now we can do a check to ensure that our demands are within our capacity. So on our westbound approach, which had more traffic than our eastbound approaches, so is critical here, we had a green time of 22.5 seconds, and we had capacity, our mu, of 0.472 vehicles per second, and that gives us 10.6 vehicles per cycle capacity. Our demand was our 60 seconds times our arrival rate of 0.166 vehicles per second, and that's 10 vehicles per cycle. Since 10 is less than 10.62, our capacity is greater than our demand, and we're good on our westbound approach. Looking at the northbound approach, we can do a similar calculation. We have 37.2 seconds of green times in capacity of server rate of 0.472 vehicles per second. That gives us 17.6 vehicles per cycle capacity. Our demand is our 60 seconds times our 0.22 vehicles per second, and that's 13.3 vehicles per cycle. Since 17.6 is greater than 13.3, our capacity exceeds our demand, and we're okay. There'll be no spillovers.